December. I hope you had a good Thanksgiving break. I certainly did. So, a couple of reminders / announcements. Homework 5 is out there, and I know many of you already started doing it, and you guys have, many students have just skipped ahead in the lectures and gone through what we are going to cover through this week and use that to solve homework 5. Not a bad idea. Are there any questions about the homework? At this point, you should be able to at least do the naive based question, and to some extent also if you want to do the extra credit question on convexity, you should be able to do that. And at the end of today, I hope you'll be able to get done with the experiment section as well, leaving us only with EM, which maybe we'll try to at least get a big part of it done in the next lecture. Are there questions about what you've seen so far? Yes?
Can you remind us what the assumptions made by the naive Bayes are other than independence?
That's the only one. But it's not, it's not arbitrary independence, it is conditional independence of features given the label. Because independence, you have many random variables here. You can think of each feature as a random variable and also the label as a random variable. So when you can't just say independence, you have to say conditional independence of features given the label.
So it's saying like, given one feature that won't affect the likelihood of any of the other features of theory?
Now, given a label, if I tell you that the label is something, two features are going to be independent of each other, and independent in the formal probabilistic sense. So probability of one feature given the label, so one feature, probability of let's say feature 1 given the label and feature 2 is going to be just probability of feature 1 given the label. So that random variable does not depend on other features given the label. Yes?
Is it safe to say instead of making an assumption, we're approximating the true probability with this independent probability?
You could think, sure.
Because you said it's kind of dense within that space.
Right. You can say that you are trying to approximate it. Sure. And I somehow prefer the usage of assumption because it makes it very clear that you are not trying to, the true function that you are trying to find may not exist in your search space. So the assumption that you're making with naive Bayes is very similar to assumptions that you may make about hypothesis spaces. So it fits in the same class of choices.
And another question, you said that naive Bayes gives you a linear classifier,
Uh-huh.
but it's a subset of linear classifiers.
Yes.
Right? Is the advantage of naive Bayes the fact that you can do map learning with kind of a prior?
Well, you could, so we'll see in logistic regression later today that you can do map learning with even a prior with logistic regression. The big advantage of naive Bayes really is that learning is trivial. You can perform learning by just counting, and that is because of the strong independence assumptions. Most learning algorithms don't have that property. Other questions? Yes?
Does it make sense to calculate the a posteriori probabilities directly from data?
The a posteriori probabilities of what?
Directly of the map.
I suspect the question you're asking is not what you just said, because I think there's a deeper question there.
No, I mean, we don't expand the map equation into the likelihood and a priori. We just calculate the a posteriori part.
So, are you talking about learning or prediction?
With the learning.
Okay. So, in map learning, you have some prior over the model times the likelihood of the data. Whereas in maximum likelihood learning, you assume that the prior is uniform, prior over models. You don't have any information about any preference over of one model compared to the other. So now given this, can you repeat your question?
So we have the probabilities of the A plus square probability is the probability of a label given the observation,
Yes.
given the feature.
Yes, and that's prediction. Yeah.
So we get these by going through the data. We see each combination of the label and then each combination of the features.
Oh no, you don't go. You want to actually get. Are you saying you want to do that, or are you saying this?
Is it possible?
Oh, it is. In fact, that's the base optimal classifier. So, given a new example, you never have a model in. You never have a fixed model. You use the data to directly estimate. Given at prediction time, you don't do any learning. You just take a new example. You have your entire training set. You marginalize out every model possible and directly estimate the what do you call it, the label probabilities. It turns out this is computationally rather tedious, but that's the best classifier you can get. But it doesn't work. I mean, it doesn't work for computational reasons.
You mentioned, and maybe somebody else asked this, you mentioned the deadline would be submitted for the project to...
Yes, in fact, that's a good point. I have actually updated the website
Oh, okay, good.
just about 30 minutes back.
Okay.
The deadline will be the last day of the exams. If I remember right, it is the 16th. Unless anyone contradicts me on 16th being the last day of the exam, we'll say it is the 16th. So that's the deadline for your project reports. Yes. So you get another week or two, maybe. Week, actually. Yes.
Do we need to submit our program code and data?
No. I just the way I'm thinking about the project, it's supposed to be like a paper where you're not submitting your code or anything. Your paper must be self-contained. Based on what you have written, I should be able to understand what you have done and make a judgment about whether it is reasonable or not. So it should also tell me what the problem is. Everything about the thing should be self-contained. I do not want to see your code. Not you specifically. I don't want to see code. I would rather read reports. And many of you are working on data that just cannot be shared for either you can't upload it anywhere, or maybe it's proprietary. So, yeah.
Can we expect some feedback?
Yes. Wait, you want feedback after the project's done? Absolutely. Yeah, I will be. What do you call it? I'll be adding notes on Canvas, and if necessary, if you actually want extra feedback, you can email me. I'll be happy to.
Is there some sort of example project report that you could point us to that we could kind of just say, oh, this is what he expects?
Okay, I'll try to make up one. Like I said, what I expect, the ideal expectation is like a research paper, but I'll try to find something that's reasonable and yet not as complete as paper, for example.
Last day of exams is the 18th.
It is?
Yep.
Okay, then the project was due on the 18th. And right now the website says 16th, but it will be the 18th.
Do you want this project dated?
Do I want project report? I need a PDF. I don't care how you make the PDF. I just want to be. Yeah, sure. I don't care. It should be legible. I mean, I really don't care so much about the details and the beauty of your report. I just need, remember that there's a human reading.
If I remember correctly, 16th is actually a Wednesday and we don't have class that week, so...
We have an exam on 16th.
No, but will it be due? It's, I think it's supposed to be during class or...
No, the exam week is a different setup. I noticed another question somewhere here. There was a lot of discussion and it's all resolved. Excellent. Okay. Yes.
Just to make sure, so we have the normal exams or final exam period that's
On the 16th, and the class website actually says
It's 16th.
Final
Final exam 16th.
Our exam's on the 16th.
Yes.
Yes, our exam's on the 16th. And do you remember the time?
We're 1-3.
1 to 3.
1 to 3. It's 1 to 3 in this room. Yes. And the project is due, as you said, 18th at midnight. Other questions? So just to summarize what we had, exams on the 16th, 2 hours. We'll cover everything from learning theory. The project's due on the 18th at midnight. Homework 5 is due on the 8th. So clearly you guys have a lot of work. But on the bright side, hopefully most of the work is already done. Okay, that was instructive.
I thought you were going to say the final would be easy.
I've taken the final, it is easy.
You also said you complete homework 1 in 45 minutes.
Did I? Oh well. Anyway, so let's continue where we were. Where we left off. We are still talking about naive Bayes. I'm going to wind up naive Bayes now and talk about generative and discriminative models. That will probably be the last big topic we are covering. Meaning, when I say big topic, I mean a fundamentally important idea in machine learning. We'll be looking at other things also. Another update. I had to modify, given that it turns out we're going a little slower than I planned. So, and I'm not complaining about that because I'm happy actually going over details rather than just covering everything that I can. So, the downside of that is that I might have to trim some lectures at the end. One question that keeps coming up, pretty much I was telling someone this morning, I had to teach multi-class classification in my office hours like about 4 times. Because many of you, it turns out, are doing multi-class classification for your projects. I encourage you to go over the slides because it seems like we just are not going to have time to cover everything. But if you're doing it for your project and you have not yet already contacted me, please look at the slides. They are on the website and should be, if they are not, I'll put it up somewhere. Right. So today we're going to talk about naive Bayes, wind up the discussion, talk about discriminative and generative learning, and talk about a discriminative classifier that is probabilistically trained, namely logistic regression. It's my fond hope that we'll finish logistic regression today, but we'll see. Just to remind you about naive Bayes, I'm going to walk through an example of how one might apply naive Bayes in a silly problem where we have to, well, it's an important problem where you're given a document, say an email, and you have to predict whether the email or document is spam or not spam. And in order to, and just let's say that for sake of entertainment, let's say that we are going to train a naive Bayes classifier for this. And the input to this problem, unlike what you've been doing in your, say, homeworks, is not a feature vector, but just a document, an object. And so the first thing that you need to do, and this is generally a lesson that you probably have to do this, many of you are doing this in your project as well, you have to extract some features. Because you need some vector valued representations of your inputs to actually throw into a learning algorithm. So the first question that you have to try to answer is, what are the features? Let's try to brainstorm some features for documents. Some of
Words
you
in your document?
I'm sorry?
The words in your document?
The words in your document. That's an excellent feature. And this is probably the most popular feature set that's used for this kind of text classification.
To go further, the word count
Word?
of each word.
Yeah. So how many times does the word apple appear in an email versus how many times, and for every word. So you get a histogram of words.
Like the sender address.
The sender address, actually that's because you know it's an email, you can have sender address and some other features from the sender. One more.
Phrases?
Phrases. Excellent. So effectively we have many options to represent these things. And it doesn't matter how we represent it. In all cases, at the end of this process, we would have some function, and by function I mean a computational function, a method that takes an email, a document, and produces a vector. Now, since we have decided that we are going to use naive Bayes, everything else is basically already solved for us. Learning is to estimate, basically estimating probabilities, and classification is to find is done by finding which label has the highest higher probability for a given document. For naive Bayes, and this is mostly just to remind you, for naive Bayes, we make an assumption, a rather strong assumption it turns out, that all features are conditionally independent of each other given the label. Now, especially for a document classification task, clearly this assumption does not hold, because documents are written in human language. The words are not really conditionally independent, because your word choices are not completely independent of each other, either given the label or even otherwise. But we'll just make this assumption and run with it. And after making this assumption, now we have to actually build the classifier. We need to train, we need to estimate two sets of probabilities. The prior for the label, which is simply how, even before you see an email, what's your belief that the email is spam or not spam? Now, I have not seen a spam email in many, many years, so my belief that an email is spam is rather low. So, and then for every feature, we need to estimate likelihoods, the class conditional likelihood, probability of the feature taking on a certain value, given that the label is spam or not spam. So those are the things we need to learn. After learning, and even forget after learning, we are going to learn a function h and b that takes x. X in this case is the featurized version of the document. It takes the input and produces a label after learning is done. The way it produces a label is to basically iterate over all labels, basically look for the argmax over all the possible labels. In this case, there are only two, spam and not spam. Iterate over all the labels and find the label that has the highest posterior probability. Find the label that has the highest probability of label given the input. But we know that by Bayes' rule that's equivalent to this expression here, and we can throw in everything that we know about our independence assumptions, and we can make a decision. So this is the naive Bayes decision rule. The prediction is the label y that maximizes this quantity, which is the product of the prior and the likelihood. And the likelihood itself is decomposed into a product over all the features. In this thing, I've got d features. Okay, so someone pointed out that an example, one way of representing documents is to basically use words as features. So it's a sparse, very, very sparse vector, because most documents don't have very, very few actually unique words. Let's say you're given n labeled examples. You're going to now the naive Bayes learning, maximum likelihood learning for naive Bayes, after going through this whole process, which I'm sure you've done now in the break, which I asked you to actually derive maximum likelihood estimation for naive Bayes. After going through that process, the estimation of the prior is simply the probability that an email is spam is the number of spam emails divided by the number of emails. Totally reasonable thing to do. Probably that it's not spam is just 1 minus that. And then for every word in the vocabulary, because our words are our features, for every feature, for every word in our vocabulary, we need to identify that that word is associated with spam. Probability that that word is present in a spam email is simply the number of times that word is present in a spam email. Ignore the plus 1 for now. The number of times it's present in a spam email divided by the number of spam emails. The probability that a word is present in an email that is not spam is simply the number of times the email is present, the word is present in an email that's not spam, divided by the number of times the number of emails that are not spam. Okay? And there's a little bit of extra here, which is called smoothing, and this is the thing that I mentioned right at the end of the last lecture, which allows for the fact that some words are just not present in your training set. Does this mean those words get 0 probabilities? That's a bad idea, because at prediction you're going to take products and you don't want zeros when you take products.
They don't use the feature space as the dictionary, do they? Do they actually narrow it down?
No, it's the dictionary, right?
The entire dictionary?
The entire dictionary. But there are interesting programming tricks to make sure that you don't have to store everything. Because you can be, for every unseen word, this value will be the same. So you just need to store it once. So you have, if your training data has 100 words that are realized in the data, you'll have 101 counts or estimates of probability. One of them is for all unseen. It's just these are just computational, just programming tricks, but in theory, it's for every word in the dictionary. Because that's your feature set, right? The dimensionality is the size of your dictionary. Yes?
Couldn't you throw away the features that are uniform throughout your whole training set?
Oh yeah, sure, you could do that. Yeah.
So then you would just be left with the set of words that actually show up in your training set.
Yeah, but then the problem is that right. So if there are many ways of actually making this more efficient. But what I've got here is just the vanilla version that we can just. If you don't really care about memory and time complexity, you could go ahead and implement it. Yes. So what we have here is basically a recipe for a spam detector that's Naïve based. And it turns out this actually gives a fairly robust spam detector, nowhere as good as what you might have, say, for example, on Gmail and stuff, but still it's actually a fairly robust spam detector that you can just implement today. And so this is just an example of how Naïve base works. Are there questions before we move along? Yes.
How can we decide the method about smoothing?
How can you decide? Say that again.
Why we use this kind of method to smooth? Why we plus y?
Oh, so right. Oh, that's a good point. This is just the simplest form of smoothing. It's called Laplace smoothing. What you're assuming is that your counts start not at 0 but at 1, right? For any word, all these counts they start at 1, and why 1? There is actually there are multiple ways of explaining this. One way of thinking about it is actually the smoothing comes from a certain prior distribution over these probabilities, and it's a particular prior. In the absence of any information, if for example instead of n training examples, you had 0 training examples, these two counts will be 0, which means your probability will be 1 over the size of the vocabulary for all words, right? In the absence of any information, you push towards that. It could, and that's just one, and you push towards a certain distribution. There are other ways of doing this. For example, you can add an epsilon. You can have an epsilon in the numerator and epsilon times the size of the vocabulary. That basically says you are pushing lesser probability mass onto unseen words. Or you can have 1,000,000 and 1,000,000 times the size of vocabulary, which says you're going to push a lot of probability mass onto unseen words. Effectively, what you're doing here is you're taking probability from seen words and distributing it to unseen words. And this decides how you're going to do that. It's a hyperparameter that's just most often, the most convenient choice is 1. There's a big cottage industry of literature on smoothing. It's actually very interesting, and many illustrious people have invented their own smoothing algorithms. And it turns out good smoothing is actually important. By the way, when I say good smoothing, there's also a smoothing algorithm called good Turing smoothing. It's not good as in good Turing or bad Turing. Alan Turing invented it, and another person called Good, his last name was Good, actually wrote it up. And so that's another smoothing algorithm. This is Laplace, named after Laplace. So there are many ways of doing smoothing. Yes?
Is smoothing like a type of reconstruction? Like you're saying you have samples and you're trying to, you're saying that just because you haven't got a sample from somewhere doesn't mean it doesn't exist. So you can reconstruct the original distribution.
Okay, that's one way of thinking about it. I prefer thinking of it as allocating probability mass for unseen features or unseen events. Okay, so this is the last thing I want to mention about naive Bayes is about its decision boundary. So the naive Bayes classifier, at the end of the day, doesn't matter that it's probabilistic or anything. End of the day, it's still going to take an example, and which is a vector, by the way. Take a vector and assign a label. So we can ask, how does the naive Bayes classifier carve up the input space? What's the decision boundary? Which examples does it label as positive, and which does it label as negative? So to do that, to see this, let's consider the simplest setting where we have two classes, plus and minus. After learning, the classifier will assign the label plus if the posterior probability of plus is more than the posterior probability of minus. In other words, the probability of in other words, it assigns this is the posterior probability, this is proportional to the posterior probability of plus, and if that is greater, then it will assign a label of plus, right? But that's the same as saying it assigns a label plus if the ratio of this quantity, the left hand side, divided by the ratio of this is greater than 1. Right? I've done nothing, no magic here. Now, here's the interesting bit. This is literally the decision that the naive Bayes classifier makes. If this ratio is greater than 1, then it gives a label of plus. What we can do now is take log and simplify. And I'm not going to write down the whole thing. In fact, there's actually it's a very easy proof. It's just a bit cumbersome, and it's going to be an explosion of sigma and product operators. And I've written it up, and there's a note on the class website. You should check it out. It's so easy that that there's no reason you should not try to prove it yourself. All you have to do is just take log of this ratio here, and the naive Bayes classifier effectively says the label is positive if the log of the ratio, so it is positive if p of 0 given x divided by p of outside. If this quantity is greater than 1, it's positive if this ratio is greater than 1, or in other words, if the 1, actually it is less than 1 in this case, because I put a 0 on the numerator, or equivalently, the label is positive if the log of that quantity is less than 0. It just so happens the log of the quantity is actually a linear function in the features. So what we are getting now is the decision boundary of the decision that the naive Bayes classifier makes is simply the following. If some w, there is some w, that w is clearly a function of the probabilities, some w transpose x plus b is greater than 0, then the naive Bayes classifier says plus. If that quantity is less than 0, then the naive Bayes classifier says minus. Which means the naive Bayes classifier is actually a linear classifier. Remember, the direction of the statement. The naive Bayes classifier has a linear decision boundary. Doesn't mean that every linear classifier is a naive Bayes classifier. It's a very easy proof, the fact that naive Bayes is linear, but it's important because it turns out you're learning a linear classifier. It's just another way of learning a linear classifier. So we're back to where we started, I don't know, maybe somewhere in the third or fourth lecture of the class. We wanted to learn a set of functions. In the naive Bayes universe, we made all these funny assumptions, ridiculous assumptions about independence and done maximum likelihood and all that stuff, and we're back to linear classifiers. Okay? The reason this is important is because the naive Bayes classifier definitely cannot express any function that is not linearly separable. In particular, if your data looks like the XOR function, then there's no point in using naive Bayes to learn that function because it's not linearly separable. Couple of, yes?
Is it still a linear separator when you have the prior map?
Is it? Yes, it doesn't matter which prior.
Because this is maximum likelihood, right?
No. Are you talking about learning or prediction? Prediction is always maximum of posteriority. Prediction is always probability of the label, the posterior probability of the label given the input. Prediction is always,
so no matter what the prior is, it's always a linear.
Yeah. Yeah. In fact, the prior probability of the label taking a certain value, which is simply this P of y term, log of this quantity becomes the bias. Did I see another hand? Yes.
Is it the independence assumption that makes it linear?
Yes.
Okay.
Yeah. It's the independence assumption that makes it linear. Okay. So a couple of other things about the naive Bayes classifier. So far, in most of the examples I had, we spoke about the features being discrete, Boolean. It can very easily be extended to handle continuous features or features that are numbers, natural numbers or integers or something like that. Because the only thing that will change is if the feature is a Boolean, then you use a Bernoulli random variable for the probability of a feature taking a certain value. Probability of feature, basically a coin toss. Either the feature can be a plus or a minus. If it is a continuous random, if the features are continuous, then all you need to change is to look up which probability distribution can express continuous random, let me rephrase it. All you have to do is use a probability distribution that can express probabilities to continuous spaces. So, what's an example of a distribution that can assign a probability for all real numbers? The Gaussian. The Gaussian distribution gives me a probability of, all you have to do is specify the mean and the variance, and you know what's the probability of some number, the random variable taking on that number. So, another common variant of the naive Bayes classifier is the Gaussian. If you have numbers, you can use Poisson distributions and so on. So basically all you're doing is changing the probability distribution that you're using, and each of them will be parameterized by some its own natural parameters, so those will be the quantities that you'll learn. So if these values are all Gaussian, then you can use what you will learn will be the mean and the standard deviation. So let me wind up. Naive Bayes works because, or not works, but naive Bayes is the classifier where you make this independence assumption that features are independent given the label. And this is a very strong independence assumption, but it has some interesting and often very useful properties. The most convenient thing about this assumption is that it makes learning very, very, very simple, maximum likelihood learning, because all you have to do is just count. It also works for continuous random variables, and if you feel like going on a little bit of an adventure, not a very big one, I encourage you to derive the whole naive base probabilities for when features are, Gaussian. There will be no surprises, I can assure you. And in fact, if the actual answer that you get looks surprising, then you know you're wrong. Prediction for naive base is done via map or maximum a posteriori. Simply that means, in English, all that means is you find the most probable label for a particular example. And you define probability as all these, as coming from what you learned. Couple of important things. The first one is, if you are ever implementing naive base, you should absolutely do smoothing. Because if you do not do smoothing, that means you're basically just giving up on features that you've not seen before. Especially if your features are discrete. So smoothing is crucial for implementing naive base. The second thing to remember is the independence assumptions that naive base makes may not be valid. In fact, very often it will not be valid. And yet this classifier has an annoying property that despite the independence assumption being clearly violated, it just seems to work. Work-ish, not quite, because it's not always the best classifier, but it always gives a reasonable decision, especially in problems involving very, very large feature spaces. And the final thing you should know about the naive Bayes classifier is about its decision boundary. The decision boundary is linear, which is important because now it lets you think about what kinds of functions can naive Bayes express, and more importantly, what it cannot express. The naive Bayes classifier simply cannot express any function that it cannot represent. So not express, you cannot learn functions that are not linearly separable using a naive Bayes classifier. Questions about, yes?
So naive Bayes is linear, but are all probabilistic methods linear?
No, absolutely not. This is discovering that this is a linear classifier is a rather special property. You can always make things linear by going to higher dimensional spaces using the feature blow-up trick. But that's not what I mean when I say no. But in general, this is a rather special property.
How much tolerance does it help for like almost linear doesn't make sense.
Yeah, I see what you mean. Instead of maximum likelihood learning, you might have to do maximum a posteriori learning, because there you will end up having to trade off just like the regular. You need something like a regularizer, and maximum a posteriori has that effect.
Sorry to go back to me again, but anyway, say you have some data set and you see that data set is linearly separable, but you could use, SVM or
Sure.
Is it basically just, finding a different kind of linear separator that's being minimized according to some different type of class function?
Well, yes, in this case it's maximizing the probability or minimizing the negative log likelihood. It is doing that, but if you ask me what I will do, say you give me a data set, and I know nothing about the data, all I know is it's linearly separable. Or all I know is it looks like it might be linearly separable. And if you ask me which classifier, which learning algorithm I'll use, very often I end up favoring either SVM or logistic regression, simply because it allows me control through better control of generalization through the regularizer. The one place where naive Bayes becomes very, very useful, there are two places where naive Bayes actually becomes useful. One, when your data set is so large that running multiple epochs over it is out of the question, then maybe I'll just do one epoch on it and throw it at MapReduce or something just to get the counts. But even there, maybe it does not matter because if your data set is so large, you probably have enough examples for good generalization even for SVM. That's one caveat. The second caveat is the naive Bayes classifier actually is very, very interesting. It falls under this family of classifiers called generative models, and those are easy to use when you have missing labels, when you have examples that do not have labels. Unsupervised learning. These are very, very easy to use with unsupervised learning. We'll talk about unsupervised learning when we start talking about EM, and generative models let's just say the math is a little easier with generative models. So I'm going to stop answering questions because that's a good segue, because we're going to talk about discriminative and generative models next, and discriminative and generative learning in general. So for say the first half, but for most of the semester, what we saw was there's some fixed distribution of examples, of instances, and there are labels. There are some slight minor variations. Either the distribution is over just the instances, meaning the distribution is over x, or the distribution is over x cross y. These are closely related but not identical, but that's okay. There's some fixed and unknown distribution over examples, and you're given a sample taken from this distribution. And we always have been looking at learning as finding a hypothesis in some hypothesis space that minimizes some notion of loss or error or something, and we may throw in a regularizer because it has all those good properties. And in general, the guarantee that this style of learning gives is that if you minimize loss on the training data, learning theory guarantees that you will have reasonable performance on future examples. This is basically a one-slide summary of a large part of the semester. And really what this means is we are approximating this function that goes from x to y, that's equivalent to somehow estimating probability of y given x. Because if you are approximating the function and you have the distribution, you are basically estimating that probability. Or it's not the same. If you estimated probability of y given x, you would have that decision function. These class of models are called discriminative models. Effectively, in a discriminative model, what you are doing is learning how to make the prediction. You really don't care about what the distribution of the data is. You don't care about how the examples are laid out in the space. You only care about making predictions. And in other words, what you're doing is just discovering, using data to discover the decision boundary. Right? That's all you care about. You don't care about how the examples are laid out. You are learning probability of y given x. A generative model is a different class of models which explicitly models how examples in each associated with each label are generated. In other words, for this generative model, you learn probability of y and probability of x given y. Basically, you learn the probability of xy as opposed to just learning. So in a discriminative model, you learn probability of y given x. In a generative model, you learn probability of x, y. In the first class of models, you only care about how to make the prediction. You don't really care about how the instances exist in nature. In a generative model, you want to learn how each example is created and a label is associated with it. Turns out the naive Bayes is a generative model. You're learning both these quantities, probability of x given y and probability of y. When you multiply them, you get probability of xy. So let me give you an example. And, or in fact, let's explore this a little more. Naive Bayes is a discriminative model. Why? Because it explicitly says, naive Bayes is a generative model. Naive Bayes is a generative model because it explicitly says how examples are generated. And this is also called the generative story of the data or according to the model. First, a label is chosen. Some label is chosen, and this label is chosen according to the prior distribution, P of y. Now, having seen this label, the first feature is drawn from this distribution. The second feature is drawn from this distribution, and so on, till the entire feature set, the entire feature representation is drawn, and the assignment to all these random variables, every circle here is a random variable, the assignment to all these random variables produces one example. When you want to generate another example, again, you first generate the label and then generate each feature independently. Turns out this is also a Bayesian network, those of you who've seen that before, but that's okay. If you've not seen it, it's fine. So, the big differences are, in a generative model, you learn P of xy. In a discriminative P of y given x. A generative model explicitly characterizes how the data is created. When I say data, I mean both the instances and the labels. A discriminative model only cares about a functional characterization of the decision boundary and does not care about how examples are laid out. So, for example, just as an illustration, say this is the circles here are your data, and there's some separator that separates them out into blue and red points. It just so happens that the data, the instance space, has some regularities across it. There are these clumps of red points here and there, and you may want to. So there are some clusters of points here. There's these things, and there are all these regularities in the underlying instance space. But today, suppose we only care about separating the red and the blue points. A discriminative model or a generative model will explicitly try to model these input regularities in addition to the decision boundary. Okay? A discriminative model doesn't care. A discriminative model only tries to model that one decision boundary and not about regularities that may be present in the input. So if you want to build a predictor, you only care about the predictor, you're better off training a discriminative model because you are learning less in some sense with the same data. With a generative model, you're trying to learn more. Not only are you trying to characterize the decision boundary, you're also trying to characterize all these basically irrelevant clusters in the instance space. There are many models that, each of these families have many learning algorithms. Naïve base is a generative model. The logistic regression classifier that we see next is a discriminative model. There are other versions. You might have heard of hidden Markov models. They are generative, and their discriminative cousins are called conditional random fields, and so on. But before we move on, the important thing to note is that the discriminative model characterizes only the decision boundary, whereas the generative model characterizes the entire layout of the data. Questions about this? And it may be a little confusing, but it's an important difference, and there's a very clear distinction between these two. So, questions?
Where would we categorize something like the perceptron algorithm?
The perceptron is a discriminative model. You don't really you don't really care about how examples are laid out. You only want to model the decision function. Perceptron, SVM, they are all effectively discriminative. In fact, so far, pretty much the only generative models that we have seen are Naïve base and the least mean square regression, where that had its own generative story.
What about nearest neighbor?
Oh man, that's a complicated setup. Nearest neighbors is more messy because it turns out nearest neighbors also like a discriminative model, because you really don't. you don't necessarily care about how you can't generate examples using that model. Using a generative model, you can basically, once you have the probabilities, you can start sampling examples from it.
Making up examples based on the probabilities.
Yeah. Nearest neighbors doesn't necessarily let you do that, but then there are some variants, so. Yeah. Other questions? Other questions? Going once, going twice.
Is restricted both machine and generative model?
Yes, it is. Other questions?
What was it you said?
A restricted Boltzmann machine, which we have not covered in this class at all, but it is a class of models. Alright, so given this understanding of discriminative and generative models, we're going to now move to logistic regression. It turns out logistic regression can be seen has many interesting interpretations, and it's actually a nice culmination of many different threads that we've been seeing through the semester. And effectively, one way of presenting logistic regression is that it is the discriminative variant of the Naïve-based classifier. That's how I'm going to start, and then point out that you can learn logistic regression using maximum likelihood and maximum a posteriori. And it turns out that learning logistic regression using these things takes us back to learning as loss minimization, which ties up this whole thing very cleanly. So let's move to that part of the story. So we have seen linear models. We have seen how learning can be framed as minimizing loss or regularized loss. We have seen how learning can be framed as maximizing some basically probabilistic criterion, like either the a posteriori, maximum a posteriori or maximum likelihood. And as an instantiation of the Bayesian learning, we have seen how the Naïve-based classifier works. What we're going to do now is somehow bring up, I'm going to introduce a new probabilistic model. Another probabilistic model called the logistic regression classifier. And it has interesting connections to Naïve Bayes. We'll see how to train it, and hopefully this is going to be a tough act to finish in 25 minutes, but we'll see if I can get back to loss minimization by the end of today. So the setup is something that we've always been looking at. We're doing binary classification. We have instances which are vectors in d-dimensional space, and the labels are plus and minus 1. And we have examples. A training set that consists of m examples. Suppose instead of thinking of it as classification, where we want to predict a -1 or a +1. Suppose instead of classifying, say I want to actually predict the probability of the label being +1. Right? So instead of actually predicting the output, say I want to predict the probability of the output being a certain being plus. One way of thinking of it is, instead of searching for functions, if you want to predict plus or minus 1, we have to search over functions whose range is plus and minus 1. Instead of searching for functions that are plus or minus 1, let's search over probability distributions that can give me a number between 0 and 1 for a particular input. So the original problem was search over all functions that took Rd, the d-dimensional vector space, to the set -1, 1. Instead of that, we are going to modify the problem and search over functions that can take the d-dimensional vector space to the range 0 to 1. And we will then pretend that that range is actually a probability. It's just a different hypothesis class. It's just a different set of functions, right? And what we have done now is, the original problem was classification. The set of outcomes was discrete. We have taken that and converted it into a regression problem, where the set of the output space is now real value. Remember that regression is when the output is real value. There are many such functions possible, right? I mean, we are looking for all functions that can take you from d-dimensional space to the set 0, 1. There's an infinite such set of functions, so we have to restrict the hypothesis space. And for logistic regression, the hypothesis space is a set of all functions of this form, set of all sigmoid functions. So what you do is the logistic regression classifier is characterized by a weight vector W. When a new example comes in, remember you still care about predicting that the probability that of that example is the probability that the label for the example is 1. And we'll predict the probability in the following way. You take the example, take a dot product, that example with the weight vector, so W dot x, and then pass it through the sigmoid function, 1 over 1 plus e power minus that quantity. This sigmoid will take a value between 0 and 1, and we'll pretend that this is a probability. Okay. So effectively what you're doing is we take a linear function, W dot x, and make it nonlinear, squash it effectively. And that's what we are going to call logistic regression. By the way, this function sigma is called the logistic function. It belongs to a family of functions called sigmoid, and they are called sigmoid because they have an S shape. So first question, what's the domain and range of this function?
Domain is all real values. You plug it into an exponential, and the range is 0 to 1.
The range is 0 to 1. Why? Because if z is negative infinity, I mean, first of all, this is an increasing function, so we only need to characterize the endpoints. If z is negative infinity, then e power negative minus negative infinity, this becomes infinity, 1 over infinity is 0. If z is positive infinity, this quantity becomes 0, so you get a 1. So the function looks something like this. It's this S-shaped curve, and it has some rather interesting properties. Just for your amusement, I'm going to list one of them. It turns out if you take the, by the way, this is not just for your amusement, it's also important for you when you take the derivative of the logistic function for your homework. But in any case, the derivative of this function, and I'm just going to rush through this a bit, is the derivative of the sigmoid function at z is simply the product of the function itself times and the 1 minus the function. It's just a curiosity. I mean, this function has some interesting properties with respect to derivatives that make them rather, on one hand, sometimes very annoying and sometimes rather useful.
Question?
Yes?
Thinking about the fact that sigma z takes a value between 0 and 1, it almost looks like the derivative is saying is the variance
Yes.
at one point.
Yeah, you can think of it that way. You could, but this is, there's some caveats here, but yeah. Okay, now let's talk about how we may predict probabilities using the logistic regression. The probability that for a particular input, the probability that the label is 1 is simply sigmoid of w dot x, which is simply 1 over 1 plus e power minus w dot x. The probability that the label is 0, or the probability that the label is minus 1 in fact, is 1 minus the sigmoid, because these two things have to add up to 1. These two things have to add up to 1. Right? So you can do the math and you get another expression for sigmoid, but I can just simplify this by dividing throughout by e power minus w dot x, and it really looks a lot like the other quantity here. Compare those two, the only difference is the sign here. When y is positive, the sign here is negative. When y is negative, the sign here is positive. I can just take them both together and probability that the label is y for a particular example is simply 1 over 1 plus e power minus ywx. So to see that this holds, consider the case when y equals plus 1. When y is plus 1, you get 1 over 1 plus which is the same as this quantity here. When y is minus 1, the minus disappears and you get this quantity here. So this very in one line summarizes what's the probabilistic model that the logistic regression makes. Questions?
So this is just an arbitrary definition of
We have just made this assumption. It turns out this is actually a very reasonable choice, and we'll see that once we start comparing this to the naive Bayes classifier.
Does the weights have a physical significance in this kind of a system?
I don't know what physical means, because it has a physical significance to the extent to which your features have a physical significance.
I try to say, linear classifiers that you had that you describe the decision boundaries, so you are linear natural.
Right.
So here, what is?
It's exactly the same. Turns out this is also a linear classifier. I keep playing this game on you. I introduce a new model, work through a bunch of math, and then it turns out we come back to linear classifiers. This is also a linear classifier, and W is exactly that one, same thing.
So I may have misheard it. So the W's, when we had SVM and perceptron, and we were working with data zero, they converged, and they were basically the exact same weight vector in the end.
Okay.
Without the transformation for the feature.
Sure.
If we were to do this with if we were to do logistic regression on data zero, should we converge to the same weight vector, because that's...
It won't be identical, right? I mean, there are minor variants, but it will be pretty much the same.
Then could you potentially just train using SVM and then use logistic regression to get the probabilities?
Oh yes, that's actually, you're not the first person to ask that question. There have been a couple of papers on this, and the general lessons are, you can train using whatever method you want, whatever linear classification method you want, plug it into what is called the logistic function, and you'll get something that you can then pretend is a probability. There is this slight annoyance that these probabilities actually have to be calibrated, and there's a question of calibration, because you may get an S curve that is too sharp, and that makes things a little bit more messy. But yes, the first version of this is you can just throw in the squashing function at your dot product and pretend that it's a probability. And it is done very often. And was there another question somewhere here? I thought I saw one. Okay, so say we care about predicting this quantity. First point to note, it's a discriminative function. It's a discriminative classifier because we are explicitly modeling y given x. Nothing here gives us any information about p of x. We don't know anything about p of x from this. We are just given the w, we are explicitly modeling y given x, so it's a discriminative model. The second point, how do you predict the label? How do you predict the label? Say I don't care about the probability, say I care about the actual prediction rather than the probability that the value is 1. What you do is you compute the probability of 1, given the example. If that value is greater than a half, then you say that it is positive. If that value is less than a half, you say it's negative. Effectively this is like a coin toss. You toss a coin that is specially designed for this particular example, and if it lands heads, you say heads.
It will be over 50% when W transpose X is 0. Right?
Yes.
And so it's the exact same comparison we're doing from perceptron.
It's exactly the same. In fact, that's a very important point, so I'm going to repeat it. And in fact, even try to derive it in the little space that I have. So, we're going to predict y equals 1 if this quantity is greater than or equal to half. If this quantity is greater than a half, that's basically like same as saying 1 over 1 e power minus w that's just by definition. But I can write, now I can just do some math, algebra. If this is greater than half, that means 1 plus e power minus is less than 2, or e power minus w transpose x is less than 1, or there was an equal to, so let's carry that on. E power minus w transpose x is less than 1 is the same as saying, that's space. I can take log on both sides, and I basically say get w transpose x is greater than or equal to 0. So what we are doing, we are predicting 1 if this holds. Or equivalently, we are predicting 1 if this holds. In other words, our prediction is simply the sign of this quantity, of the dot product. That's the answer to your question. The decision boundary is simply this line.
Now, suppose you wanted to say, okay, if I'm too close to the boundary, then say like my probability is between 0.75 and 0.25.
Sure, let's say your probability is 0.51.
Yeah, so suppose it's in some range that you declare. Maybe you could do like, ask a question and say,
yeah,
I don't know about this one, could you...
Once you have these kinds of probabilistic estimates, you can actually use the probability to do other interesting things. Definitely. But it turns out you can also do that if the probability is 0.51, using the same transformation, W transpose X should be something very close to 0.
So you margin.
It's exactly that. It's exactly, in fact, it's like a margin. It's basically the distance from the hyperplane has a one-to-one mapping to the probability through this transformation. Okay, so that's the geometric interpretation of logistic regression. If you care about predicting the label using as the one that, if you care about predicting the label via maximum a posteriori, in other words, you predict the label that has the highest probability, then what you are effectively doing is, separating the space using a hyperplane. Now, to answer the question about why this is, why this particular function, one way of answering that question is to see its connections to naive Bayes. And so remember that the naive Bayes classifier is a linear threshold unit. Probability of y is the ratio of the log probabilities is some line. Right? And I didn't prove it, but I stated it and encourage you to prove it for yourself. But I also know that these two terms at the numerator and the denominator are not independent of each other. Because they should add up to 1. So I can just plug it in and separate out P of y equals 1 in terms of the W, and you actually get back the sigmoid function. Turns out the naive Bayes decision boundary is also a sigmoid, just like logistic regression. And the jump from here to here is just take these two terms, get rid of the P of y equals minus. That's all you have to do. So the important lesson, so what we have here are two things. One, this is a reason for the choice of sigmoid. Why is logistic regression using sigmoid? Because it turns out the naive Bayes is also doing the sigmoid, has a sigmoid decision boundary. And it's a reasonable thing to do, except the most important thing to know is in logistic regression, we do not ever care about P of x. They have the same posterior distribution over the outputs, except naive Bayes is trained is a discriminative one. It's trained to predict the probability of xy. Just so happens that once you have the probability of xy, you can do some algebra and get the probability of y given x. But it's trained to predict the probability of x comma y. The logistic regression classifier is only trained to predict the conditional probability y given x. So in some sense, this is actually why I like to think of naive Bayes and logistic regression as being a discriminative generative pair. Their decision boundaries are the same. Their final posterior probabilities are identical. Just so happens that one of them is trained in a discriminative fashion, the other one is trained in a generative fashion. That's really the only difference between these two models. Questions?
So does logistic regression have the independence assumption?
It turns out, once you go from, if you explicitly only train directly fit this function, you don't have that problem.
So is being a generative model as opposed to a discriminative model a negative thing? Is it a negative thing then?
No, I don't think so. In fact, this is almost like a philosophical discussion. I am more biased towards the discriminative side of things, but that's because in many applications, you don't really care about the probabilities. You only care about the actual prediction. And if you only care about the actual prediction, might as well just only learn the function that predicts. But don't take my word for it. There's a whole camp of people who believe that discriminative models are garbage. Because the reasoning goes as follows. There is no reason you should only care about the prediction. You are trying to, as a person who is modeling the problem, you are trying to model the problem. You are not trying to sell a program that makes prediction. And if you want to model the problem, you should model both the entire probability distribution, x comma y, not y given x. And that's the philosophical version of the story. Another reason why discriminative models are useful, and this is what I mentioned before, they are much easier to work with when you have latent variables. When you have aspects in your data that, when you have random variables in your examples that are not annotated by people, when you have missing data, then these generative models become more useful. You might have heard of things like topic models, latent directly allocation, LDA, or another one is latent semantic analysis. These are all generative models. They are widely used. And the reason these things show up is because topic models give no annotation for the topics. And you're just supposed to discover regularities in the data. The only way you can discover regularities in the data is if you model the entire data. So it's really your perspective. It depends on what you want to do.
Once you have a weight vector, can you translate back into a naive Bayes model?
Not always. Not every linear model is naive Bayes. Every naive Bayes is a linear model. Because of this condition here, these things have to sum up to 1. And that may not always work. Okay, so in the 5 minutes that are left, I'm going to quickly show you how to train a naive Bayes a logistic regression classifier. There's some possibility I may not get to the end of it, but we'll see. Let's go to learning. Studying is always, it's the same. We are given some training examples, and this time we care about learning the probabilities, but effectively we care about learning a weight vector. And maximum likelihood estimation is simply the same as finding a weight vector such that the probability of observing this particular data set is maximized. We know that our examples are IID. What do we do next? Yes, so we write down the likelihood function. We care about probability of the entire data set given a vector. And because they are IID, this probability is simply the product of each example. Each example is XY pair, and so that's exactly the same thing that we've been seeing before. And the next step, and this is again like part of the recipe, is don't work with products, work with sums or take logs. So maximizing the quantity on top is equivalent to maximizing the sum over the log probabilities. Right? Okay, so we want to maximize this quantity. But we know that P of y given x, according to the logistic regression model, has a certain shape. So we can just plug it in. What we get is maximize, just substitute this into the definition of P into the expression on top. We are finding a weight vector W that maximizes the sum of minus log 1 plus blah blah blah. Right? So this is maximum likelihood estimation for logistic regression. How do you solve this problem? How do you solve this maximization? Some of you may have already implemented it. You can take the derivative, but then you're going to take the derivative over m, a summation. Is there a better idea?
Do stochastic gradient descent.
You do stochastic gradient descent. You should be able to do stochastic gradient descent on this now, because we've seen it a couple of times, and this is just a different function. You take the derivative, you pick a random example, pretend it's the entire training set, take the derivative of this quantity here, go in the negative go in the opposite direction of the steepest ascent. So, or in this case, you're maximizing. So it's this, you're climbing up a hill. You're not going into a ditch because you're maximizing, not minimizing. We could also do. This is maximum likelihood estimation because we are trying to maximize the likelihood. We could also do maximum a posteriori estimation. And this is probably the only time we'll see map estimation for a real problem. Map estimation is simply saying, I don't know, I have some idea, some preference over different weight vectors. I have some way of, given if all other things are equal, then I have some way of saying I like this weight vector more than the others. And the maximum a posteriori estimation requires you to specify a prior function over weight vectors, over hypotheses. Suppose each weight vector, each element of the weight vector, each weight is drawn from a Gaussian whose mean is at 0 and it has a fixed standard deviation sigma square. So this assumption gives us a way of writing down the prior. The probability of W, each weight is independent, so we can just write the probability of the weight vector as simply the product of the probabilities of the individual weights. It comes from a normal distribution, so we can just plug this in. It's an assumption we are making, and this is the prior. What we are saying is, in the absence of any information, this function decides how much I like a particular W. And the W I like the most is the one that maximizes this quantity. In particular, the one that you like the most is actually 0, because this quantity becomes the maximum when each Wi is 0. So let's do the same thing in the 2 minutes that are left. I'm going to step through maximum posteriori estimation for logistic regression, and I have the map estimation on the side just for comparison. We have a prior, and the big difference between map and maximum likelihood is earlier we only maxed we tried to find a W that maximizes probability of S given W. Now we're going to find maximize this quantity, the product of the likelihood and the prior. We play the same game again. We substitute everything in, take the log, and plug in the actual definition of the logistic function, and you get something that looks very similar. In the maximum likelihood estimation, you maximize this quantity, that's the same as this here. In addition, you have another term that comes from the prior. And I'm rushing through this mostly because I actually want to get to the end of this, but it should not be terribly, it's roughly similar to what we've seen before. You are maximizing the sum of some negative quantity and another negative quantity. Or equivalently, you are minimizing the sum of two things. Where have we seen this before? This must look awfully familiar. Many people saying things. One person.
minimizing the loss and recognizing.
Exactly. What we have is, this looks a lot like minimizing a loss term plus a regularizer. It turns out this is a different loss function. It's not SVM, it's just a different loss. It's the same regularizer. And this is the probabilistic interpretation of the regularizer that we saw before. The way we came to the regularizer before was we said we like to maximize margins, and maximizing margins is exactly the same as minimizing this quantity. If you are a Bayesian person, what you'll say is, I don't really care about margins. I don't know anything about margins. What I do care about is actually introducing a certain particular prior on my weight vector. Namely, every weight is drawn uniform from the Gaussian distribution, centered at 0. And you do maximum a posteriori estimation, it just magically becomes this regularizer. This must look a lot like SVM, except for the box. And there's some constants that are traded around, but that's, that's okay. So you should be able to write down stochastic gradient descent for this. In fact, you will be implementing stochastic gradient descent for this for your homework. There are other learning algorithms. Sometimes you'll run into an algorithm called LBFGS, that stands for Limited Memory Broyden Fleischer Goldfarber channel. You will never be asked that question. But you don't really want to know what, you don't care at this point. You should probably focus on getting stochastic gradient descent to work. Alright, I'm going to stop now. And the next lecture, I'm going to continue where we left off. Go back, just do a quick summary of learning as loss minimization. Now that you've seen logistic regression, you should be able to piece together a lot of things that we saw through the semester into one slide effectively. We'll go back to perceptron, SVM, AdaBoost, and logistic regression, and we'll see all of them in one slide. Alright, and we'll do the EM algorithm in the next lecture. I have office hours and such good things, so